Hi there and welcome to the screencast for the workshop for week 12 for GIS and Spatial Stats. So if we just go through to the material and save the workshop sheet in somewhere we can remember it. Here it is. We'll go to RStudio and we'll open that up. Okay. Put our name there. Oh look, I don't have a package installed. Might as well install that while we're there. Okay, so we're looking at Spatial Interpolation today. Let's just see how that installation process is going. It's ticking over, that's good. We'll wait for that to finish. Quite a bit to install by the looks. And we're done. Right. So we'll load our packages. Our data is from on BATS, so it's from this paper here. You can click on that paper if you can follow that link if you'd like to the paper. So it's published. So read. Hranic was the main author. Done with Dave Heyman and myself and a bunch of other co-authors from the US. It's on white nose syndrome and bats. So white nose syndrome is essentially a fungus that can grow on the bats while they're hibernating in a cave, and it essentially makes the bats come out of torpor. So torpor is where they lower their heart rate right down when they're in hibernation, and it forces them to come out of hibernation early, and then which requires a lot of energy, and then they have to go back into hibernation because it's not, it's still winter, and so they come out of hibernation and go back in, which uses a lot of energy, and many of the bats don't survive. And we want to predict the likely survival of bats across the North America, and so as part of that, we wanted to know what the average mass of a bat was in various places across North America. And because of course the heavier that the bats are, the more fat that they have when they go into winter correlates with the amount of energy that they can use over winter, and therefore how well they deal with the infection. So we're going to read in our data. So we've got a CSV file with our bats and their masses and so on. We've got a boundary file of North America, and we're going to specify the CRS is just the same as our North American boundary file. And we're going to use a Lambert conformal conic projection for the area, and here it is here. So I'm using ggplot with geom.sf just so I get some nice plots using the Lambert conformal conic projection that sort of makes the land area approximately correct. If you were just using plain WGS 84 or latitude longitude on a flat plane, then of course this area up in the north here gets very stretched and looks a bit weird. So for example, if we just drop this coordinate transformation and redo the plot, you can see it looks rather strange. Okay, so this is just to make it look nicer. Right, we'll redo that. We have some covariate information in order to predict the mass of bats. We have it's likely to depend on the climatic conditions. So bats that live in colder areas will of course put on more weight because they need to have that extra mass, that extra body fat in order to survive over the winter, whereas bats that live in areas that don't have as longer winter, for example, will be lighter because they don't need that extra body mass over the winter. So the climate information is from the Adapt West project. There's the link there if you want to have a look. And I've taken it and down-sampled it somewhat in order to make it a little bit easier to work with today. So we can see that we have some geometry here, and what I'm doing here is so this is it's tiled, so it's like a raster, if you like, across the region in latitude and longitude. And what I'm doing here is I'm renaming the geometry feature as to be tile, so that we still have the tiles, and then I'm recreating the geometry feature as the centroid of the tile. And the reason I'm doing that is that point geometries tend to work a lot better for interpolation, particularly for creaking. So that's why we use that. So if we go across here, we'll have two geometry columns. The geometry column, which is the main one that will be used, which is basically the centroid of each tile, and then we've got a polygon column, which is the rectangles for every location. Okay, so we can plot these, some of these variables. So we've got, you can see here, we've got elevation, we've got northing, we've got frost days, we've got freezing days, growing days across the year. And so we can plot these. And so this, for example, is freezing days. So you can see further north there's more freezing days than there is down in the main continental US. Though of course through here, where I think this is where the Rockies are, there's higher amount of freezing days, right? So this is using the tile geometry. If I didn't have the geometry equals tile in here, we'll just use the default geometry, which will be the points. So we can see what that looks like. Let's have a look. Fill doesn't make any sense, so we'll have to use color. So that, I think, will then work. There we go. So you can see that it's using points. So you get the same type of thing, but it's a little bit nicer with the tiled geometry. A little bit smoother looking. Right, so let's perhaps have a look at some of the other things. So you can see here that that perhaps the freezing days does correlate with the size of the points. So where the points are larger tends to be where the number of freezing days is perhaps a little bit larger. We could try with some other things. So let's look at frost days. Perhaps we'll use a Viridis scale for the fill. So here's frost days. Perhaps there's some correlation there as well. Elevation. So here's the main Rockies through here. And that doesn't really correlate all that well, does it? Because we've got points with large mass that don't have high elevation, right? So these are inland points where, of course, on the plains in Canada, where you're going to get a lot of a very long winter, so they'll have to survive for quite a long time, but it's not high. Okay, it's sort of on a plateau, so it's definitely low compared to the mountains in the west there, and perhaps northing. So northing, of course, is just going to be our it's just going to give a smooth gradient, and that perhaps correlates, but I think the freezing days tends to correlate a bit stronger. Okay, so northing, frost days, freezing days all correlate with bat mass. Elevation doesn't. Presumably growing days would as well. Let's have a look. We haven't seen that. So this will probably inversely correlate, won't it? Yeah, so maybe growing days inversely correlates. Essentially, that's sort of the opposite of the number of freezing days, presumably. Growing days also correlates negatively with bat mass. Okay. So what we want to do now is we want to estimate the bat mass across the entire region. So we want to take our bat mass at these locations here and interpolate so that we have it across the whole region. So there's three methods we're going to use. We're going to use inverse distance weighting. we're going to use simple kriging and universal kriging. So we'll start with IDW. One thing to note here is that there's two functions IDW. So there's one in the GStat, which is the one we want to use, and there's one also in the SpatStat package, which is the one that we don't want for this work. So if you run this next code and get an error, it may be because you have a SpatStat loaded, and so you can change that just by going GStat ::. So I've got an error here that I'm missing a package. I'm missing a package here, so I need the stars package. Install that first, so I'm just going to go to the packages menu and install stars. So stars is another spatial package which is particularly useful for converting between the different spatial formats. So we have the SF format, simple features, but we also have the spatial formats such as spatial data frames and so on from the SP package. And so stars is a way of transforming between the two. It's its own spatial format. So hopefully this will all install and we can get it all working. It's taking a wee while to compile, but hopefully hopefully we finished shortly. And then we'll be able to run the code. If you're on a Windows or a Mac, it'll just install directly the binary version. It'll be nice and quick, but I'm on a Linux machine here and it's installing from source, so it has to compile it. There we go. So that's some geometry packaging. And now stars is installed. Okay, so now we're working. Perfect. And so here is the output from IDW. So inverse distance weighting, essentially what we do is we take it, so to interpolate at a particular location, we average across the locations at which we've sampled. So we average across the locations in space that we have the bat mass. And we weight those, in the average, we weight the observations that are closer higher than the observations that are further away. Okay, and we're weighting them in terms of the distance squared. So the IDP here is the power used. So it's the weights are 1 over the distance squared. And you can see the output is we have a geometry column like we from our NA point. So we've got the location. So this is the location of the bats, and this is the new data that we want to project to. So this is our point data across North America. And so we have all of the points in North America here, and we have the corresponding predicted bat mass in the var1 predict. var1.var is just full of NAs. It's not useful here. We'll use that when we do kriging. So we can plot this in the same way that we did before. There it is there, and you'll see that it's only plotted because at the point locations. Because we don't have the tile geometry to use. So so we've lost the additional columns that we had in NA.point. So NA points is up here, and we had all of these extra columns here, including this additional tile geometry. But we've lost that. All that we've got is the point geometry and our predictions. So if we want our tile geometry back, we need to rejoin this spatial data set that we have here with the predictions back to the original NA points data set in order to get that other information. So this is what the spatial join here does, this ST join. So if we have a look at na.idw.tile, here it is here, we now have our two columns from our prediction, but we also have all of the other stuff that was in the previous data set, including the tile geometry that we had, which has a so we can map the geometry to tile and get a nicer looking plot. So you can see here that we've predicted the bat mass across the entire region. Okay, so the color within the circles here, where the bats actually are, is likely to be close to the true color. So the true mass, and then in between we've interpolated. Okay. So we now have an estimate of the bat mass everywhere. And so in our original paper that we were writing, we could then use that in an energetics model which basically simulated the process of the bats going into hibernation and being infected and coming out and going back into hibernation and so on, and computed the amount of energy that they would use, and then we could relate the energy to the mass and figure out whether they were likely to survive or not spatially, so we could get a sort of a map of whether they're likely to survive based on where they are, so that, for example, further sampling could be done in those locations to determine whether they were in fact surviving or not, and potentially interventions could be put in place. Okay, now this IDW backup here, we used a power of 2, and that is something that you can supply. You can decide what you want to put in there. Smaller powers, so smaller than 2, will result in more smoothing. Essentially what you're doing is that if the power is smaller, then you're weighting observations that are further away a bit higher than if the power had been higher. So essentially you'd get more smoothing. If the power is larger, you weight them less. Okay, so down here we'll try redoing it with IDP1. So let's copy and paste the code from further up. So let's grab that. So this is going to fit the. We'll use ID power 1. We'll change that to a 1, and then we'll plot it. So we'll join it back to our spatial data frame. And plot it, grab all that, so do the interpolation, and then we'll spatially join it, and then we will plot it. Okay. And here we go, this is the surface we get here. And it's a little bit smoother than the one we had up here. Okay, now you've got to be a little bit careful because the scale will be different. So notice that the scale is only goes up to 10 here, whereas it goes up to 12 here. I could perhaps change that by altering the scale so that they're the same on both plots. So let's do that. We'll say that limits is equal to C. So we're going to go from, say, 5.5, maybe, or a bit lower than 5.5. Let's have a look here, so 7's in there. So we'll go from, say, 5 to 13, just to make it easy. Okay. So there it is there, and then we can put the same limits on our one down here so that we can, so they're actually directly comparable. Okay, so you can see you've got much more smoothing here than you have here. Okay, simply because the value that that we're predicting here is going to depend on this point way over here a lot more in this plot than it does in this one. Similarly, if we change the power to something bigger, so we change it to, say, 4 and rerun, then we'll get more local smoothing. Okay, so we get less smoothing overall. The value in the neighborhood here is mostly determined by the one point there, and it's not determined by the points further away as much. Okay, 2 tends to be a happy medium. So we'll write a little bit about that here. It doesn't overly smooth like a power of 1 does, but still allows some smoothing, increasing the power to a bit higher gives even more prominence to the local data. A power of 2 seems a happy medium in this case. Okay, so that's inverse distance weighting. Now we'll move on to Kriging, and the idea with Kriging is essentially that we the weights that we had which are basically proportional to distance here, is the same no matter where you are, right? So if you're down here, or if you're in here where we've got quite a lot of data, then the points that are distance, 100 kilometers away will all be used. The same applies here, where points 100 kilometers away would be used, but there are none of them, right? So really what we'd want is more smoothing in these regions here, where there are not as many points. So you'd want to upweight the points that are further away there, but you'd want to downweight the points that are further away where we've got lots of data, right? So that's essentially what creaking allows us to do. And to do that, we need to fit a model that relates the variation in the measures, so the variation in bat mass, to the variation in the distances, basically, right? So what we do is we look at the point-wise distances, so the pairwise distance between locations of bats, and the variation between the measures at those pairs, and that's what a variogram does. So let's have a look at that. So here it is here for the bats. So this is relating to semivariance, which is the gamma. Essentially, it's the squared difference between bat mass at pairs of locations, and this is the distance between the pairs. And you can see that it doesn't look as pretty as the plot did for the zinc concentration data. And part of that is just that we have really not many observations here. We've only got 42 observations of bats. So we don't have all that many pairs. There's 1,600 odd pairs, and they're stretched all the way across the continental US and Canada. So they're really far apart. So it's quite hard to build a variogram in this case. But you can see that maybe there's a hint that the variance is lower here, and then it gets higher and jumps about a whole heap. So we might be able to fit some slowly increasing variogram in this case. So we're going to choose an exponential, and it's going to have a range of 3,000, which is this range up here. So we're going to be going up to about there, and it's going to have, we're fitting a SIL of 1, which is probably a bit low. We should really choose sort of 3 or something, shouldn't we? Let's change that to 3 and see if we do a bit better. And then we've got a nugget of 1, which seems about right. So let's try fitting that. So you can see that the actual nugget was 1.27, and the SIL was 2.8, and the range was 1,200. Okay, and that's the shape. So it's not a great fit, but it's probably fairly reasonable. We would expect the correlation, the error in the bat mass at locations that are very close to vary quite a bit still. I mean, it's an animal species. So we'd expect our measurement of bat mass to vary quite a bit, so that sort of makes sense. And we'd expect the variation at large distances to be larger, right? If the location of bats are very far apart, then they shouldn't really be related to each other very much. So this is something that might be sensible. It's not we really need to collect more data here. That's really what it comes down to. Right. So once we've got our variogram model, we can then throw that into the creaking procedure. And this gives us essentially the same output as the IDW does, right? So for every location in our new data set, so in every location of our points in North America, that's the geometry column there, we have 2 columns. One's the predicted bat mass, which is var1.pred. And the other one is, because we fit a statistical model here, so we have some error associated with it that we can characterize, we can actually characterize the uncertainty directly. So this is the variance in this measure here. Okay. So again, we can join it back to our original data set with the ST join here, and we can plot it. Let's plot it on the same range. What was it? 5 to 13. And so there's the creek surface. So you can see that it is smoothing a bit more than the IDW did, but a bit less than, so a bit more than this one, but a bit less than this one. So it's somewhere in between. Now the nice thing, of course, is that we can get our uncertainty out of this. I don't think I've written about this here, but we can perhaps add a code block. By plotting the var1.var variable. So let's take that same plot, but instead of plotting var1.pred, I'm going to change it to var1.var, and perhaps we'll use a different color scheme. So let's try scale fill distiller. Is that the one I want? Let's have a look. So what I want is I want a sequential scale. Yes, I need to specify the palette. And which one do I want to choose? Let's have a look at the options down here. So sequential scale, let's choose this one. Just to make it different from this one, basically, right? I don't want to use the same color scale for everything. Okay, so here's our uncertainty. So as you can see, the uncertainty is low, right? The colors are darker where we have data. And the more data we have, the lower the uncertainty is. And the uncertainty is highest where we're interpolating. So you can see here that where we're extrapolating, rather. So you can see here that, you know, down here in Mexico, we don't have any data at all. And so it's saying, you know, it's giving us an estimate here as to what it is. The estimate's about, what, about 8 or something. But it's saying that actually the variation in that measure is very strong because we don't have any data there. So be cautious about our prediction there. Same with up in here. We're going to need to be cautious about our prediction because we have no data there. In fact, bats probably don't live up here because they probably can't survive the winter length in the higher latitudes, particularly inland. So that's quite useful for giving an idea of the uncertainty in our prediction. And we could incorporate that in any other modeling that we do, right? Okay, so that's where we have no covariates being used, where all that we're using is the location of bats and their mass. And we're just smoothing across the region of North America. But we do have some covariates available, and those covariates, of course, are measured everywhere in North America. So we could potentially use them to predict what the bat mass should be. And we can do that basically non-spatially by just looking for correlation. Right? So before, for example, we saw that there was a correlation with freezing days and growing days and so on. Here we can see that when we just plot the points, right? Now the correlation here isn't strong, but there's a decreasing trend between growing days, increasing growing days, and mass. So as the growing days increases, the mass tends to go down. Now it's not a very strong relationship, but nonetheless it's there. Okay, let's do some other plots. I've obviously made a typo here because this is perhaps supposed to be freezing days, but let's do them all. Let's make this freeze days. Okay, it seems to be a stronger relationship with freeze days. There's a few outliers though. So let's do plots for the other ones. So we could do freeze days, growing days, and frost days. And we could do some other ones as well. Let's do northing and elevation. Have a look at them all, see what we can see. Okay, so here's they all are. So elevation doesn't seem to have anything going on, right? It's mostly flat. In fact, there seems to be two groups, right? Those that live in the low elevations and those that live in the high elevations. Northing, again, there doesn't seem to be, maybe there's an increasing trend, but again, we have some outliers. It's not very strong. Frost days, again, these outliers here, but maybe there's an increasing trend within this subgroup. And maybe a decreasing trend with growing days, which is probably just inverse to freezing days, isn't it? You can't grow things when it's freezing, right? So which some variables do we think are most useful? So probably the freezing days is most useful. This will be when the bats are hibernating anyway, so presumably bat mass will be fairly strongly correlated with this. Bats in regions that have longer winters will be heavier. They have to be to survive. Right, so now we could test some of these using a linear model or regression. So the LM function fits a linear model, and you give it a formula. So the formula has this little tilde, which basically means in terms of. You put your outcome variable of interest on the left and your covariates on your right. Right, so this is saying I want a model for mass in terms of freezing days, where the data is taken from our BATS data set. So here's our model for freezing, and you can see that we've got some estimate of the y-intercept and the slope. So this says that the mass, so when the number of freezing days is 0, the mass is about 7 kilos, and it increases by 0.02 kilograms, or about 27 grams, I guess, for every 1 day increasing. And that is statistically important. So the p-value here is a measure of statistical importance. Okay. We do note that that the multiple r squared is around 0.2. So this is basically the proportion of variation explained by the covariates in our model. Okay, so this is saying that about 20% of the variation in the bat mass is explained once we account for the freezing days. So we've explained some, but not heaps. Okay. So we could try linear models for frost days and growing days as well. So let's just copy that block, modify it accordingly. So we're going to have frost days instead of freezing days. So we'll call this mod frost. Have a look at that one, and we'll also have one for growing days. Mod grow, and maybe just for fun we'll do elevation as well. We know elevation doesn't correlate at all, does it? So we'd expect no. So these names here that I'm calling objects are just arbitrary. So let's run all that. Okay, so we get lots of feedback. Maybe we'll do one in each block. We'll do a separate code block for each one so we can talk about them separately, perhaps. Okay, that might be the best way to do it. All right, so the first one, we can see that, so this is frost days. So again, there's an increasing trend with frost days, so which is important. It's a little bit less important than it was up here. So the p-value was 0.003 here. It's 0.004 there, but nonetheless, there's some correlation. The multiple r squared is a little bit lower accordingly, so we're explaining about 19% of the variation. For growing days, we have a decreasing trend. It's important, but not super important. Our p-value is getting a bit larger, and consequently, we're explaining less. So we're explaining about 10% of the bat mass can be explained once we account for growing days. And presumably, there's not much going on at all with elevation. So we explain basically nothing, less than 1%, and there's not a significant effect of elevation. Okay, so freezing days seems to explain the most variation in bat mass, around 20%, followed by frost days, around 19%, and growing days, around 10%. What was it? 9%, 10%? 10%. Elevation doesn't explain much at all, so it won't be useful. Okay, and potentially we could put more than one thing in our model, right? So we could put both freezing days and northing, for example, or freezing days and frost days and northing. We could put them all into a model in order to sort of explain a little bit more. So let's just try that, just to see what happens. This wasn't intended to be done, but let's see what happens. Let's take our model that's pretty good, and let's chuck a couple of other things in it. So we can include more than just one thing at a time. So mod more. For more stuff, let's add in frost days and northing. We just do that with pluses. Order doesn't matter. Put in any order you like. It won't make any difference. And there we see. So if we put all of them in, we can see that only freezing days is actually seems to be important, but we do explain a bit more stuff. Okay, and the reason is that all of these things are correlated with each other, right? So when you add both freezing and frost in, for example, the importance of freezing day is conditional on frost day being included, right? So if you've already accounted for frosting, then you would have covered a lot of the freezing information anyway, right? So the sort of the incremental advantage of adding freezing over frosting is actually pretty small. So that's why its p-value is a bit higher than it was before. And you can see that the incremental value of frosting over freezing and northing is not important, and northing over the other two is also not important. Nonetheless, by having that extra stuff in the model, you explain more of the variation. Right? So perhaps, even though these aren't actually statistically important, it might be worth including them anyway in our estimate. Perhaps we'll try that further down as we play around. So I'll just write a little bit about that. So by adding more things into the model, we explain more variation in bat mass. Now, 28%. Note the significance of individual covariates should be interpreted as being over and above the other covariates, i.e. does freeze days make a difference if we've already accounted for frost days and northing? Yes. The p-value is 0.04. Similarly, does northing make a difference after accounting for frost days and freeze days? Not really. The p-value is 0.12. Right, it's a bit higher, so it's not telling us much more. Because all of the things are correlated, that's kind of what we'd expect to happen. They're called collinear. That doesn't mean we should drop them out, as the goal here is good prediction, i.e. we should count the R squared value more than the individual p-values for covariates when determining the best model to use. Okay. Right, so perhaps we'll have a look at see how this model does when we do kriging later. Okay, so now these models here that we fitted don't account for any of the spatial correlation. So they only so they assume that each of the measures is independent, which of course we know that they aren't, right? Values that are close to each other will have similar bat mass simply because they're close to each other. So you've got similar bats there, right? We need to fit a variogram and so on in order to have this. So here, this is our model for freezing days. So that's the formula that we've put in. Perhaps we can make this clear by saying the formula that we're going to use is equal to that. Okay, and then we can just put formula in here. Right, so that fits our variogram. We then plot our variogram. Okay, so you can see here that this is actually a bit of a better fit than we had before. So here I'm using that same exponential model. We're underestimating the variance right at this very large distance, but we're fitting the rest of it reasonably well. And so now we can do creaking with the same formula. Right, and then plot. Let's put it on the same scale, just so that it's similar to what we had before. Okay, so you note that now we're actually, our estimate up in this top area is actually off the scale, so it's shown in grey. Okay, so we've burst through, we're estimating over 13 kilos for bats if they lived up here. Again, we could look at our uncertainty. So this is what this code block here does. We're using that same palette. Oh, slightly different palette. This one, let's use the same one I had before. What one did I use last time? I used yellow, orange, brown, just so that we're consistent. You can play around if you want to find the one that you like the most. Here we go. So notice our variation is actually on a fairly similar scale than we had before. Okay, back up here. Where is it? Here we go. The variation was actually a little bit less when we just did simple creaking than it is now. And part of that would be just because we used a statistical model that didn't explain very much. It was only explaining 20% or so of the variation. And so when we extrapolate that statistical model, that's going to have a lot of uncertainty at the edges. So most of the uncertainty is in fact up here, right? In the middle here, we're actually down in the sort of the 2s, maybe the 3s at a stretch, right? So we actually probably got less uncertainty than we had before. Just for fun, let's try our more complicated model with frost days, freeze days, and northing, just to see what happens. Let's see if we can get it to work. I haven't tried this, so this might go badly wrong. So let's grab our code for our variogram first. So we'll change our formula to formula big, maybe will be our freeze days plus frost days plus northing. We'll use our formula big and we'll go big dot, we'll call this model big. Right, update all the variables and let's see if we can fit this thing. Yeah, okay, so that still fits okay. Right, so that's good. So now we can do our actual plotting. So we'll grab that code block to do our creaking. Okay, so we're going to go big creak. We're going to use our formula big for that, and we're going to use our big covariate model. And then we're going to take that and join it back and create a big model tile set and do the prediction. Right, that should work. Okay, so here's our prediction there. We can compare that back to our other one. So it doesn't look too different. There's a little bit of difference up in here. And also down through here, there's a little bit more detail on this one than there is on the other one. What about it? The uncertainty? Presumably the uncertainty will be a bit lower because we've explained more, right? Our R squared was higher. So let's take that same code block. And we'll switch to our var1.var instead of prid, and then we'll grab our other color palette so that we remember the uncertainty, so we can see the uncertainty on that same scale. Okay, there it is there. So yeah, we've actually, interestingly, we've got more uncertainty up here and more uncertainty down the bottom, probably because we're at the sort of at the extreme of our model here. But through the middle, we're probably actually fairly similar. Perhaps we could try these on the same scale and see. Let's try limiting it to so perhaps we could limit it from, say, 0.5 up to 4, maybe. So this will show there'll be a bunch of stuff that'll be out of range, but that's the scale, that's the uncertainty there. And let's look at the uncertainty of the model that we had back up here. Okay, so so our uncertainty is higher at the edges, but in the middle it's pretty similar to what it was before. Through this area here, I think we've actually reduced our uncertainty in this model down here. So where we have data, we've reduced uncertainty, and between it's sort of pretty similar to what we had before. I think slightly reduced, but pretty hard to tell, right? So there we go. Spatial interpolation with inverse distance weighting. Kriging and universal Kriging. I seem to have hit a memory issue here, I think, on my computer.